Let us start today's lecture by telling a few words about the superheater, which I have discussed yesterday. Just giving you the definition, what is a supervisor superheater? We have gone through the different aspects of economizer. We have know that reheater, and now we are going through the superheater itself. All these items named like this, all these are the integral parts of a steam power plant itself, and they are essentially using the additional heat extracted from the flue gases, which are not used and which are going to be wasted, and efficiency of the plant is going to be reduced. In order to improve the efficiencies, these plants, different setups or different machineries are used, which is meant for either heating the temperature of the incoming air, or by heating the incoming water, or by heating the steam generated to a certain degree which was not achieved during the conversion of heat, conversion of water into heat itself, and which will be used in afterwards in the turbine for its higher efficiency and power generation of power itself. Even a portion of the heat is being used when uh, from the extract of the turbine, which is a mixture of steam and water, and it can be used and heated to a certain degree before it falls back to the boiler itself. So basically, machineries are being used to utilize the maximum, to make the maximum utilization of heat which is generated in the different by burning the coal or other other fuels. Now, the supervisor is a heat exchanger in which heat is being transferred to the saturated steam to increase the temperature. Saturated statute increases temperature means essentially those terms are named as supervisor, which is also a heat exchanger, which is also exchanging the heat of the coming out of the flue gases created by burning the fuel in the furnace itself, and this heat is being and the heat is heat transfer in heat exchanger being transferred to the saturated steam generated inside the boiler itself to increase its temperature to a considerable extent. Initially, the steam which is already formed, which is generated in the boiler itself, is supposed to be around temperature 120 to 150 degrees centigrade, or not more than that. It is already superheated, but still that amount of heat is not required for our purpose. We need certain rise in temperature to increase the whole cycle efficiency, or better functioning of the turbine itself. So to increase this rises the overall cycle efficiency, which if the total way of the moisture content, in addition, if the it reduces the moisture content in the last phase of the turbine, and that increases the turbine internal efficiency. So it is heated to the vapor, and to increase the efficiency itself, and it is also used in the moisture content in the last stage of the turbine, so that it increases the turbine thermal internal efficiency itself. So in modern high utility means turbine is supposed to be used a steam of certain amount of a certain considerably higher amount of temperature than the boiling points, which is being supplied in the heat exchanger, and the turbine that heat is converted into the kinetic energy as in terms of the high velocity of the fluid, which is being increased on the turbine blades to convert the efficiency. But as the steam is giving the diameter, giving the work, giving this energy to the turbine blade, which is in turn rotating, the steam also losing its heat, and it should be go back before it going back. It should be maintained. Before we should maintain, it may convert it into a certain portion of water. A certain portion of it may convert it into water, which is being kept in a moisture form by this heat exchanger efficiency, heat exchanger use itself. Now, in modern high pressure boilers, more than 40% of the total heat is absorbed to generate the steam takes place in the superheater. So, large surface area is required to be provided for property of steam. We see in the boiler, in the furnace, where the heat is generated in the boiler by burning the coals and other additives, etc. The heat generated almost half of the percent only being used to heat the boiler, heat the tubes, which carries water inside the furnace, carries the water and kept inside the furnace as in the form of riser, which goes the which are making the natural circulation or forced circulation by moving the water down from the drum, its boiler drum itself, sending it to the riser where it is converted to the heat, and then a mixture of heat, steam, and water goes back to the drum again, and where uh, water content is kept down inside the drum, and steam content is went up to get the go to the supervisor itself. So it is supposed to heater superheater is be heated supposed to be received as steam only the moisture, not any sort of water particles. But sometimes it may so happen a portion of the water also being uh, boiled or converted to steam in a supervisor also. But its portion is supposed to be less, and almost 70 to 80 to 90% water content of the steam vapor, steam vapor and steam moisture, vapor and steam moisture are supposed to be reduced, kept inside the boiler drum itself. So what happens? The superheater here. So what? How we are heating from the furnace, which is all the risers tubes carrying such the water content from the air itself, from the drum itself, is being heated to convert the steam. But it is supposed to be, but only there exist the tubes are exposed from the surrounding the walls of the furnace itself, where you are getting the huge amount of heat coming out through coming out convected by means of conduction, transferred to the boiler tubes, to the riser tubes by means of conduction and convection, and also a major part of it is being transferred by means of the radiation itself. But in modern high pressure boilers, more than 40% of the total is absorbed in generated the steam takes place in the supervisor. So large surface area is required to be provided in the superheating of steam. Here what he says that 40 to 50%, almost half of the steam is supposed to be utilized in high pressure in in the mo- in the superheater high pressure boilers. High more than 40 to 50% steam is being utilized to convert to heat the steam in the in the superheater itself. And so large surface area is required to be provided for superheating of steam. So everywhere, in order to ensure the convection heat transfer, heat transfer is only three process: conduction, convection, and radiation. Mostly convection, and one form to another, it is being transferred to the heat is being transferred from the which from the flue gases surrounding the riser tubes, which is kept surrounding the total walls of the furnace itself, and majority of this heat is being transferred to the riser tube by means of the flue gases, by means of the radiation. Still, it can absorb or it can transfer only 50% or 60 maximum 60% of the heat to the uh, liquid water in going through the riser tube itself, and thus converting into steam, not to 100% but to a considerable effect. But remaining 40% remains unutilized. So you are supposed to use it in the superheater itself, which can only possible only when your supervisor has it gives a considerable amount of exposed surface to for the conduction and convection of the heat, as well as the heat also being transferred by the radiation of the heat itself. So what happens here? Superheater are generally classified to conductive superheat, convective superheat, radiant superheater, and combined superheater. So three types are there. There are how they are getting the heat, how the heat is transferred from the hot flue gases to the water or steam inside the superheater. There are all three processes are used. There are convection, conduction, and convection superheat, mostly the radiant superheat, or sometimes conduction, combined of conduction, convection, and radiation superheater. Three types of superheater is possible, which is very clearly denoted. The how we are transferring the heat. What is the method of transferring heat, either by convection, conduction, or by radiation itself? Now, depending on low heat, how heat is transferred from the gases to the steam, convective superheaters are located in the convective area of the furnace, whereas uh, usually stayed usually ahead of the economizer itself. So superheater may be of different type or different portion, or a number of superheaters are being used, well, which is placed in different portion of the furnace. Generally, a convection type superheaters are placed, as per our theory, before the economizer, which is also a transfer of heat, which is also converting, absorbing the heat of the furnace to the and send it to the water itself for this transfer. It can should be ahead of it, so that it closes to the furnace or boiling part of the furnace, where the heat is can directly convert, or the flames can be directly come into the, or if not touch the tubes, but close to the tube, so that it can hit that hit the water inside the tube to a higher extent, or hit the steam inside the tube to the supervisor temperature itself. Now, in earlier design, screened the convective superheater from the furnace radiation by a blank of water-filled tubes, which are not protected from being from combustion flames and high temperature, but also intercepted the slag particles and presented the sagging problem. So, in earlier parts, we use a number. We generally, in order to take away, keep the heat away from the from the supervised preheaters, superheaters. The heated preheated portion of the superheater, which is placed in the convection room, is protected by a water walls or water tube walls. Means a portion should show the flames of the air itself does not comes flames from the emerging out of the burning of the coal in the furnace does not come directly comes in contact with the walls of the preheater itself, because a a number of tubes also placed in between the flame and the superheater, so which absorbs this which is directly heated by the walls heated by the flames of the furnace, and the convection, we avoid the convection to a certain extent, to a great extent, to the superheater by keeping it away from the flames of the furnace itself. Now, also the slag, every water is being used at use has certain minerals which is sometimes in which is not necessary, which is created scales on the surface of the superheater or boiler walls, and we have to prevent the sagging, means coming down, or increasing volume of the sagging tubes, which is not directly coming into the not heated, so that it should not have any reaction with other materials itself to make a bigger amount of minerals on the to cover the walls of the tube itself. Now, the convective superheaters are often termed as primary superheaters, where saturated steam from the drum is emitted. So primary pumps is used because first it is superheated here, and the steam generated from the drums of the boiler comes directly here. So it is defined as it is doing this superheating works from the beginning. It is defined as the primary superheater itself, where saturated steam dermal is admitted. Although the disposition of the heating surface varies widely with the design of steam generators, means disposition but position of the heating surface that varies widely design of steam generator itself. Disposition or position of the heating surface varies widely with the design of the steam generator. A typical arrangement is shown in the figure with the next page. After convective supervisor, the After convective supervisor CSH, the steam generated, the steam produces proceeds through the radiant superheater RSH, convective superheater CSH, and this is called RSH. This is produced towards the radiant superheater, which is placed in the radiant zone of the furnace itself, near the water wall, to absorb heat by radiation. But here we are absorbing the heat, we are transferring heat to the superheater, but not in the flame, but they are not coming in the contact of the surface itself, but it is absorbing heat because it is going to the it is going to and the heat thus created is going directly hitting the contents of the tube itself. It is shown in the furnace here, shown in the uh, I mean this picture as a figure in the next page. Now, the steam leaving the refrigerant supervisor goes to the tea superheater, where highly pressure water is directly spread into the steam in such a quantity that the temperature of the steam after the last step of superheating in the pendant superheater PSH does not exceed the rated value. What we see here, the TS diagram and a psychometric chart. It is a psychometric chart of the steam. It is giving the TS as it's so. It is a TS diagram. So what we see here, one, two, three, four, the different position of the heat, different position of the heat of the superheater itself. So this is the this is portion from 2 to 3. It is the heat is added to the radiant supervisor. From the portion 3 to 4, it is added in the uh, pendant supervisor itself. And from the portion 1 to 2, heat is added as the primary superheater itself. So, so everywhere the entropy is being used, which means the heat is being added from 1 to 2 and 2 to 3 and 3 to 4 itself. And now what happens here? This is the superheaters. It's a figure of the superheater itself, where it is shown that it is the steam coming from the drum itself with the approximate specific heat equal to Ws, which goes inside and moves in the superheater walls itself and goes out with the same specific Ws, but in terms of total conversion into steam, where the uh, hot gas from the fluid is coming here, which is at temperature Tg1, and it is transferring heat by means of the say radiation and goes out to the as Tg2, which is less than Tg1. So certain high amount of heat is being transferred, and while the water, the specific volume of the fluid water or steam comes inside is the same which is going out of the steam itself. So and there is a stream pump is designed, pump is kept in the system which flows the water steam mixture and in the superheater and thus get the steam out, and that which is again sent to the pendant superheater itself. Now what is clear, before sending the superheater steam to the pendant supervisor, spray we spray the steam with we make a de-superheater of the steam itself, where we send the steam through a de-superheater where pure water of normal temperature is being straight through the steam itself, which reduces the superheated temperature to a considerable extent, and the temperature of the steam after the last stage of superheating is in the perfect supervisor, pendant supervisor, does not reach the rated value, does not exceed the rated value. It is we are supposed to keep the heat the steam from the boiling point to the superheating point, say up to the point one, up to the point four. But we should have proper content quality I mean control over the amount of over the temperature of the heat coming out of the superheater itself. Thus, it is being controlled by spraying pure water in room temperature in the speed so that it flows down the heat to the required extent, and it is sent to the pendant supervisor where this if there is any particle of this pure water keeps in the steam, it converted to steam, and the right temperature which is required to be make in the required to be right temperature of steam which is required to be sent to uh, the turbine itself is being maintained here. So superheater is but pendant superheater is a combination of superheater in the sense that it receives heat partly by convection and partly by radiation itself. The radiant and combined radiant superheater say together are often termed secondary supervisors. So the primary supervisors, which is being where which carries the water and steam moisture inside, which is placed nearer to the furnace in the convective zone, means which is supposed to be come to the direct contact of the flames, but that contact is not doesn't take place because we keep a water wall in between the furnace and between the flames and the uh, superheater, a primary superheater, so that it saves the this water wall saves the primary superheater from being directly come in contact with the flames, but direct convection of the heat to the flame. Mostly the heat is also either convection all right, but it is also convected to mostly to the sup- mostly by radiation, and most heat transfer it takes place in secondary supervisors, which consist of the radiant supervisor and pendant supervisor, which is both are mostly they run by means of the radiation, and pendant also used to a certain of convection if possible, and keeps the temperature of the superheated steam not beyond your control but keeps a specific control over its function itself. Now, the energy balance in the consecutive supervisor gives QSH. The energy balance means what is the energy being transferred from which part of the supervisor. That is quality, the QSH, the cumulative superheater, is a omega G is a specific heat, a specific weight of the water going through the superheater drum, etc., multiplied by the specific heat of the gas, specific heat of the gas itself, which is being multiplied by the change in temperature of the flue gases, which is at the entry at Tg1 and reduces to Tg2. So this is the heat transfer which takes place by the heater itself, by the furnace itself, which is equal to Qs H2 minus H1 and U0 A0 delta T log mean, which means the same specific volume of heat as we are maintaining. There is no leakage or spraying somewhere. Then the heat transfer to H2 minus H1, it is being uh, transfer H2 minus H1 is the final heat minus the initial heat, though, which is equal to U0 A0 delta T log means, which means U0 is the coefficient U0 is the coefficient of heat transfer by 1 by U0 1 by H1 plus XW by K2 plus 1 by H0, as air A0 inside area of the tube pi n pi d0 t. N is the number of tubes inside, L is the total length, D is the inside diameter of the tube. And since it's a gas to gas heat transfer, the low heat HI and higher heat low heat HI steam and higher heat H0, the overall heat transfer coefficient will be like this. And now omega S, or the specific heat, is pi by 4 dt and the outlet Vs by Vg, where Vs is the velocity of the stream, average velocity of stream in the supervisor, and Vg is the average velocity of gas in the supervisor itself. So Ws should have the area, total area into number of sort of area inside the tube, and area of the tube itself, T, and it multiplies the number of tubes itself, and the velocity of it with which it is flowing, and uh, what is the velocity of the gases with which it is coming. So Vs is the average velocity of steam in the superheater. For intermediate pressure boilers, the steam velocity may be 22 meter per second. Thus, for higher velocity boiler, it is about 12 meter per second, and for very high pressure, it is 10 meter per second approximately. The supercritical reheater thus made of tubes 50 to 75 millimeter and OD, originally tolerated or originally boilerless, and the master diameter have longer pressure stresses, and without them better. Without them, they are better. The transfer of the larger tube have a lower stream flow pressure because it has more volume of fluid. It requires more volume of fluid, so lower speed as well as pressure will comparatively reduce, and pressure drops and remains close to the alignment. There is no such the number of coils needed for flow is being estimated from above the equation 2 over, and the length of one will be L. The radius. So, uh, superheaters are heaters made of tube 50 to 75 millimeter OD, utilizes the boilers. The smaller diameter have lower pressure presses and withdraw them from better. Which are the better? Smaller amount of small diameter tubes, but no number of tubes have low pressure stresses because they are absorbing less amount of heat because of low volume, and they can the heat much better. The larger diameters have a lower steam, low pressure drops, and are easier to align. Larger diameters also have problem. A plus point is a lower stream, have lower steam, low pressure drops, and are as easier to align yourself. If the number of coils needed to flow is estimated from above equation, and the length of one will be L, is determined after as computed from equation 2. So it is important to calculate the number of coils needed for the flow and estimated from the above equation, and the length of one coil is determined from permits greater heat absorption by the radiant mode and heat transfer. Radiant flow is located in the radiant zone of the furnace, permits greater heat absorption by radiation, and method of motor of steel convey. When the furnace permits the greater heat absorption by the radiative mode of the heat transfer, which is given by the Stephen-Boltzmann equation, which is given as sigma AT into FT minus omega Ti into Tw is equal to Ws H3 minus H2, where W Stephen-Boltzmann constant 5.67 to the power minus 8, and AT total surface area of the superheater exposed to the flame means we have to calculate the surface area of one tube, and you have to multiply the number of tubes to get the total surface area exposed to the flame. If there is a difference, if certain tubes are come direct contact with the flame, which is under convection and conduction, then it will be treated separately. But mostly the tubes are kept in the superheated, the radiation zone, and thus making the matter making the steam superheated. And EFW view factor with respect to flame and wall. The view factor with respect to flame and valve, TF, the flame and outside temperature, flame outside temperature, and K and T omega is wall absolute parameters K. Parameters, so what we have, sigma civil improvement constant, delta E, delta T is the total surface area of superheated pressure, and FTW is the heat transferred between this particular period here, and temperature T1 and to the power 4 minus to the power 4, the heat drops uh, due to the heat drop or something have drop, non-use of the heat, the temperature and the temperature of the flue gas at the inlet was T1 and the outlet at T4 itself. Now, if TF is not strongly dependent on load, the steam flow increases with head, the steam transfer for unit may flow diseased. So, next page, 6. Let us start now the steam generator control. The object of the steam generator control, there are so many units, the incoming air, outgoing steam, and conversion of steam or conversion of water to steam, then to control the total function of the furnace itself by producing the heat and utilizing maximum of heat to increase the efficiency, and total the furnace are being transferred either by convection or convection or by radiation itself. Now the controller, so all these parts, so there, then reheater is there, where superheater is there. Even after the superheater, there is a preheater to control the temperature of the fluid, then to control the temperature of the steam up to a certain extent, and then send to the steam. A portion of the coming out also goes to another preheater, which is converted and keep it in the steam form itself. There's so many functions we are doing, and to provide the steam flow required by turbine at design temperature and pressure, then the variable that are controlled are one fuel pump ratio. It means the object is to required by the design temperature. The variables that are controlled are fuel, firing rate, airflow, gas flow distribution, feed water flow, and turbine valve setting. So, what are the factors which we are supposed to control so that the entire system will be well under control, and in fact, system should run with highest efficiency itself. So, what is that? Uh, the variables that are supposed to control is fuel firing rate, airflow, fuel firing rate means how much fuel is being fired for a considerable period of time, how much fuel is being burnt and fired to make the flame for power for heat, and you should have a proper control over this amount of coal which is supposed to be burnt as per our requirement itself. Next, the airflow. What should be the free of airflow? What free airflow from the surroundings to come inside and goes to the furnace itself. Then what should be its proper flow? Next, uh, the gas flow distribution. The gas flow distribution, that what how the gas flow, the gas generated from the flame itself or the smokes contains a huge amount of energy, which is being distributed in which way by providing baffle to align its direction to the particular direction which you want to go. And next is the feed water. Feed water. The water temperature is being preheated to a certain extent, because not we are using the room water temperature, because it shows that the total, it is shown that the and the how much gas flow distribution, how much flow how after the burning, how much gas is flowed in different direction, maybe how much it is being used to heat the fluid going through the different enormous amount of riser tube inside the outside the wall, and how will distribute the distribution, where will, in which portion will heat it more, which portion will heat less, and how will control this distribution of heat, either by providing wall or providing a temperature different type of steam at different interval of time, so that one type is usable at a moment and another type is usable and then at some other moment. Now, the key measurement is described. Next is the turbine valve, water valve, feed water flow to the turbine. How will you control this high temperature, high pressure stream to go inside the turbine through the nozzle, where its heat energy is being converted to the mechanical energy itself. Now, the key measurement that describe the plant performance are steam flow rate, the water, feed water and steam frame rate at and interval electrical power output. So key measure for checking what is the plant performance as equal to steam flow, as what is the flow rate of feed water, and turbine rises safely. All these three factors should be totally under your control, and it should be totally known to you. The key measurement boiler is the plant performance. uh, the control system must act on the measurement of these three plant factors, so that it remains plant operation at desired location. Sure. Now, most modern control numerically employed closed tube controls is made in this made the active output of the system is increased and compared to some demand signal set point. The difference in the measurement and demand, called the error signal, is then used to reduce the difference between temperature and set point to zero. So what we are doing in the control system, we are employs closed loop control, means control should be in a done in a closed loop. The loop should not be very long or big. Yet efficiency of control will be reduced. The actual, how do we do it? The actual output of the system is measured. What is the output of the system? Means what is the output of the power, and then compared to the same um, same demand during signal, the set point. The difference in measurement and demand, called the error signal, is then used to reduce the difference between measurement and set point to zero. So what we do, we have some set point, we have designed some demand signal or some set points. Difference between the measurement and demand cause the error signal. This then used to reduce the difference between temperature, and the set point is to zero. So set point is controlled, that is controlled by the difference in measurement, and what is the difference in measurement, what is the difference in demand. If the difference is within parallel limit, then the fluid used to reduce the then it is used to reduce the difference between the measurement and set point to zero. The proportional control is the simplest type of closed loop control. In this mode, the control output is proportional to the error signal. So what is coming out of the control, it should be proportional to the error signal. If the controller signal will be either directly or inversely proportional to the error signal, depending on the control system is. So I am finishing here up to this portion, and go for the remaining one and the next step. Thank you.